I'll be talking about PV power plant performance assessment techniques, challenges, and way forward in today's talk. I lead the PV reliability group at NCPRE, which is the National Center for Photovoltaic Research and Education at IIT Bombay. It's the biggest center for solar R&D in the country currently. And we have a fairly strong group of people and researchers working in the area of quality and reliability of PV modules. So I have a group of about 25 people that work in just this area. Okay, this is the outline of my talk. I'll be talking about some of the metrics that people use for performance assessment, the limitations of these existing metrics, some of the commonly observed issues, and some key results from the All India Survey of PV Module Reliability that NCPRE does. And then some discussion about what are the better metrics and some new techniques for PV performance assessment. And I'll also introduce something called as Indian PV CAT that we have started, which is very relevant to the agenda that Ritika mentioned, the standards for quality and reliability of PV in the country. So since this is the first talk, I think I can get away with giving these definitions. I'm sure most of you know what this is, capacity utilization factor, specific generation, that is yield of a PV plant, performance ratio. And then also is this thing some people use called temperature corrected performance ratio. So I don't have to describe these are fairly well-known things. In temperature corrected performance ratio, the only difference is that people have also added temperature in there. So you can normalize it with respect to temperature. The normal performance ratio is only normalized with respect to irradiation. The temperature corrected is also normalized with respect to temperature. Okay. Now, these are some of the factors that affect these metrics, right? So CUF is something that is not from PV, it's borrowed from some other industries. And there's large number of factors that can affect CUF. For example, grid availability, time of operation, radiation temperature, etc. Okay, and it's just what you really need is the total AC output of the plant in a given time period. Okay, and specific yield was developed by PV industry. You need daily AC output of a plant data in a particular time period, and it's basically kilowatt hours generated per kilowatt peak installed. But it is also affected by the radiation temperature of the plant and also the temperature coefficients. Right? The performance ratio, for that you need hourly data of the AC output of the plant and plane of array radiation data as well in a certain time period. But it is also affected by the quality of that radiation data as well as the temperature of the plant, among few other things. Right? And in case of temperature corrected performance ratio, in addition to PR, what you need is the module temperature data as well, hourly module temperature data. And both of these performance ratios are affected by the quality of your radiation and temperature data. I must insist that this is quite important because it's often overlooked, and when you do that, I'll share some examples of what happens to the PR and temperature corrected PR when the quality is not adequate. Okay. So what's the motivation for plant performance assessment? We need to ask these questions honestly, really. I mean, we shouldn't take it on its face because there are various motivations involved. Because, for example, one could be just compliance to minimum contractual requirements for a period of time when you own the asset. There's no desire to further improve the performance if it meets the minimum demand. Second thing could be, well, you want to just make sure there are no issues during the time period. Even if you detect the issues and they're not going to show up in the time period of interest, you may not really worry about them, right? Those are two things. The next is to maximize the profits by optimizing the plant, the lost revenue due to loss generation, and the cost of diagnostics, O&M, etc. So it's a purely economic but long-time economic view. Okay? And then there are two more things. One would be to address any kind of non-compliant performance issues down to module level during a 25-year lifetime. And the last one would be having some kind of predictive value. So to proactively identify the problems that would come up in this plant over time and then address them in advance. Okay. So PR is something generally people use, but then I want to give you an analogy. Using PR to address these, especially the last three problems, is like using body mass index for diagnosis to ensure longevity of people, right? So BMI is a useful thing. It's weight divided by height squared, but then it's not sufficient. It does tell you a few things about the fat content, but there you definitely need to do a lot of other tests to really make sure that the person is healthy. Not everything is caught by BMI. Similarly, not everything is caught by performance ratio as well as the temperature corrected performance ratio. So what are the repercussions of having a good performance ratio? Of course, on a bright side, you have compliance to contractual requirements, there's feel-good factor that a plant is doing well. And I don't know if the acquisition, during acquisition, that kind of plant would have a higher evaluation, okay? Maybe. But there are a few things. For example, how accurate is your on-site radiation data? You need to look at that, right? And there may be an issue present, but it is not yet visible at the PR level, because when something shows up at PR level, it's typically a very serious issue, okay? So these are some of the things that one has to ask if you see some even if you see good PR data, okay? What happens when you have bad PR? Typically people think that it probably needs better cleaning, there's soiling on the plant, so it's going down. Maybe it has some issues and a diagnostic team needs to be called, okay? But again, you have to look at the accuracy of your radiation data. Sometimes it could be just artificially low PR. It had nothing to do with quality and reliability of the plant as such, or the modules as such. And secondly, when you start seeing something at the PR level, it's probably too late and the problem is really widespread, okay? So using PR is good, but then it has its pitfalls as well, right? Now this is the question. So is simply having a good quality weather monitoring station, is it enough? So the answer typically would be yes, if you have calibrated things, so why worry, right? So here's something interesting that I would like to show you. This is on y-axis here, you have the DC power output of an inverter in a large plant, okay? And on x-axis you have the irradiation, okay, the global horizontal irradiance. You see that there are two interesting things here. One is this part where the radiation is actually quite high, but the power or the current is, or the power is quite low. And this part where the radiation is quite low, but the power is high. Why should you even worry about this green thing? You're getting some power for free, looks like, right? But you should, because when we did some detailed analytics on this, what we found, the issue was, this is a very large plant spread out across a larger area, and it only had one weather monitoring station. And when there was cloud movement, so this blue thing shows up when there is cloud over the solar array, and there is no cloud cover over the paranometer. So the paranometer is measuring high irradiance, but the solar array is actually not seeing that. Therefore, it is recording lower power. And on the other hand, in this case, there was cloud cover over the paranometer, so it is recording less irradiance, but the solar array is not seeing the cloud cover, so it's actually generating more power, right? So both of these kinds of points, they will result in PR, they will affect the PR at the inverter level, but they don't point towards any kind of quality or reliability issue in a plant. Okay, these are just false flags. But I must also tell you that these things were not even seen at the plant PR level. Okay, this plant had about 40 such inverters. So this kind of effect was not even visible at the plant level. Only when we looked at the inverter level, we figured this thing out. So you need more well-calibrated weather monitoring stations for large plants. That's the lesson learned here. I'll just quickly discuss some of the case studies for diagnostics. These are also again from PV Diagnostics, why their team was called and what was the issue. As you can see here, these were some of the issues why they were called, right? There was low PR, and then they found there was high PRD, and then they implemented the potential induced degradation, some kind of reversal solution there. In this case, the inverter was tripping. They found was the insulation resistance was the problem. And in this case, there was some kind of module damage, and insurance claim was there. As you can see, in all three cases, these were very extreme events when the diagnostics team was called. These were not proactive, okay? That's the bottom line. Secondly, again, you see these kinds of things when they were called for low PR, then there was inability to meet just a second, I'll get the laser pointer over here, yeah. So inability to meet the minimum generation requirement. So only in one case, a plant could not meet this kind of generation requirement. And what they found, what was quite interesting, is that the initial expectation itself was set wrong, because whoever did the initial modeling of that place used some faulty radiation data files. So the expectations were set wrong, and therefore people were thinking that this plant is not doing good, when in reality it was doing all right. Okay. So again, the bottom line is people are not really doing this proactively, or most people, I would say. and they're going for diagnostics only when something terribly goes wrong. Now I'll talk about a little bit about the module level issues that we have found in something called as All India Survey of PV Module Reliability that NCPRE has been doing since 2013. We have done 4 surveys so far. I'll just present key results to you. Because for us, if there's a problem in the module, it should be replaced. Even if you're not detecting at the plant level, it's a problem and one has to address that problem. So this is the demographics of the survey. Our team has inspected sites from Hanle in Leh to Kanyakumari, and then here in Rajasthan and Chennai and all places in India. Okay, these are modules in different climatic zones. Most of the modules belong to hot zone because that's what we see in India. And you can see that we had about 100 modules from non-hot zones and about 1,100 modules in hot zones. By the way, this was also the demographics. You can see that most of the modules belong to either poly or monocrystalline silicon. There were few thin films and HIT and IBC as well. And this is the age distribution of the modules. You can see that most of the modules were from 1 to 10 year old. Okay, and they were from ground mounted. Most of them were from ground mounted system, but few from roof, and one floating system was also there. So these are the degradation rates of all the technologies. This is a histogram of module degradation rates for all the modules in the survey, in all technologies. So just look at this figure over here, because here I have discounted for 2% of the LID, which you expect in the beginning. Remember that the financiers assume a degradation rate of 0.7 or 0.8% per year. What we found is the average was 1.22% per year for all the technologies combined. Okay. It's quite high as compared to that, and but at the same time, not everything is bad. You see that there is this tail over here, which is high degradation rate modules, but then there are significant number of modules and systems over here as well where they have low degradation rates. So we need to learn from the systems that are doing good. Since most of the modules belong to silicon technologies, this is the histogram. So just look at this figure over here, right? So you see that for the silicon modules, the average degradation rate was 1.47% per year, 1.5 we can say. Again, which is slightly higher than the total, because earlier we had thin film modules in the mix as well, and now it's just silicon. So the degradation rate of silicon was slightly higher. You see that there is again this tail which is a little bit alarming, but then there are these systems in between from where we can learn and improve. But then we also need to understand what is happening over here so that we can avoid these kinds of things going forward. So we segregated the module degradation rates as per the climatic zones. You can see over here that the modules in hot climates are actually degrading at much faster rate, about 1.57% per year, as compared to modules in non-hot zones, just 0.5% per year. Okay, and this shows that our methodology is actually very, is right, because this is the kind of degradation rate that people have received when they have inspected systems in US, Europe in temperate climates, which could be cold zones. Okay, and when we do that here in India, we also get very similar degradation rates. So for example, most of these modules come in from Leh Ladakh region, cold climatic zones. We get very low degradation rates there. And most of these modules over here come from hot zones like Rajasthan, Chennai, rest of the India, and we get very high degradation rates there. By the way, these are representative systems in India, because here I am just showing you young modules that are deployed in hot zones. Okay, by young I mean 1 to 5 year olds, right? There the degradation rate goes up even higher, it's 1.8%. And for older modules we see about 1.15%. These are large systems. So this is the kind of system that is being deployed typically in India, multi-megawatt solar plant and so on. This is what we should be aware of, and then we should also see how to reduce this degradation rate. Okay, so blindly assuming 0.7 in a plant that is going in hot climate in India may be dangerous. Right, so I'll quickly mention about the effect of hotspots. What we have found is that through handheld thermography, the hotspots in PV modules do lead to power degradation, and as you can see that when the difference in the hotspot and the module temperature reaches about 4 degrees Celsius, you start seeing significant degradation in power. Okay, below 4 degrees Celsius we have not seen any significant degradation, but after 4 degrees Celsius you do see that. We also did some drone-based IR imaging for this survey, thanks to SenseHawk and AirProbe, and as you can see over here, There are these are the drone-based images, and we also compared the similar images with handheld thermography and also electroluminescence, and we were able to detect significant problems in plants like diode failures, which result in shorting of the diode and dark this thing in the EL image. Okay, and you can also verify that from the IV curve of the particular module. However, this is something that you should remember when you are doing drone-based IR imaging, that these red points here show that the modules that were detected by drones, faulty modules detected by drones, right? So you see that when the delta T was very high, so the modules had significant hotspots, it was detected by the drone. But delta T of 4 or 5 degrees Celsius was not detected because of the settings that were used at that time. But we have seen that even these modules where the delta T is about 4 to 5 degrees Celsius should be detected, because those are also carrying signatures of high power losses in the PV plants. Okay. We also have data, this is very unique kind of data that very few people in the world have. We have year-on-year degradation data of different systems, where we are able to talk about now whether the degradation rate is truly linear or not. In a module's datasheet, you see that straight line, right? It's not based on any physical evidence. It's an assumption that the degradation rate will be linear. We have seen that in case of some plants, it's truly linear, but in some cases, it's not. It can be super linear or it can be sublinear as well. This is an important figure that I would like to spend just a few minutes on. This is a failure mechanism figure. So on y-axis, you see average degradation rates of various sites that we inspected in the All India survey, and the red ones indicate the sites where we found PID, potential induced degradation. You see that PID was the key reason why we found high degradation rates in All India survey, followed by those stars that you see over there. There are 4 sites that had stars. So there, it's unknown because we could not see any degradation signature in electroluminescence or thermal image. Okay, and that's strange because if there is a problem, it shows up in either of these techniques. So we believe that these modules may be overrated, and therefore we are seeing degradation, but in reality, it's just the initial number was higher than what it truly was. In some sites, we also found interconnect and finger damage, which can be due to corrosion or thermal cycling and some other cases. And in some cases, we had hotspots and cell cracks as well. Okay. It just shows that the modules in the tail that you see, most of the modules actually came from systems having potential induced degradation. And as you already, most of you would know, the way to detect PID is through electroluminescence imaging and then finding a correlation of this degradation rate with respect to the position of the module in the string. So we were able to see that in some strings of the same plant, the PID was not present, which was quite surprising to me because if it's the same module, then it should behave in the same way. But apparently that's not the case. So what's the best assessment methodology? I mean, these are known things, but not always followed, like having a good SCADA system and WMS, doing some analytics based on that, and also repair and maintenance. Thermography, drone plus handheld for verification of the drone-based IR. Field IV, if you have a new plant, you can use a test van because the uncertainties can be lower in those kinds of measurements. And if it's a slightly older plant, you can use field IV tracing using just the handheld IV tracers. You can also do EL and UV fluorescence for detecting onset of different degradation mechanisms. But there are these new ways now which have some predictive value. Okay, so for example, we have a setup which can predict the worst case power loss from cell cracks. If you have modules that have cell cracks, just put the module on this setup and it will tell you what is the maximum power loss due to those cell cracks the module may see in its lifetime. Okay, there are no such setups that can do that. This is a very new thing, and we are in process of patenting. There are only 2 such setups in the world, by the way. One is at IIT Bombay and entirely designed and made in India by IIT Bombay. Second thing, similar thing is what DuPont has been proposing, a sequential stress testing of backsheets, okay, which can predict whether your backsheet is going to fail in 4 to 5 years and so on. And we also have some new low-cost hardware for large-scale IV tracing of multi-megawatt power plants. So you can do 100% inspection of 10-megawatt plant in about 7 days, okay, so which is quite good. So this is just an introduction of that, the setup that we have for cracks, okay. As you can see in this graph, okay, the y-axis is actually the power loss and x-axis is the number of cycles. So for 3 different technologies of modules, we were able to design a test in which the power loss due to cell cracks eventually plateaus out. So that means that is going to be the maximum power loss a module will see in its lifetime. Okay, that can go much beyond the current IEC requirements. One thing I'll mention to you here is that, okay, so what's the solution, right? We need standards and so on, but the timeline of IEC standards is actually quite long. IEC standards is quite long. It can take long time, 4 to 5 years from issue is found to having a standard, and converting a IEC standard to BIS can take 1 to 2 more years, okay? But from identification of issue to having a BIS standard, it can take anywhere 5 to infinite years, because if we are just adopting IEC standards, then it depends on whether IEC takes up an issue of your interest. If they don't take up, you will never have a standard, okay? So therefore, we need that kind of activity over here in India, looking at issues that are of relevance to India, okay? So these are some of the things. So we need more, India needs more representation at the international standards development bodies. Currently, we are highly underrepresented, okay? And we need standards that are based on research and data, and not just ad hoc standards with harsh tests, because then they will have a lot of false negatives, okay? So we need a focus group that can generate first drafts of standards for the BIS ETD 28 committee, and that is what we have actually proposed. This is called Indian PV Quality Assurance Task Force. The vision is to improve reliability of PV through indigenous standards development, and we propose to do that by using some research and data that people have in the PV community currently. Okay, and IIT Bombay is leading that effort, but there are several other partners who are sharing data. I would like to thank my entire team for this work. This is their work I'm just presenting, and also PV Diagnostics for sharing a lot of slides. Thank you.